Cosmides and Tubi, who are really, if you see them in anything other than what I'm talking about, ignore them because they're wrong. But they on this spectrum fall around here. They're very much not the economists. Cosmides and Tubi are evolutionary psychologists. They don't believe that we're perfect rational beings at all. But they do suggest that we have something that they quote a calculus of probability, namely that we do have some deep understanding of statistical phenomena and are able to then use that understanding in our daily lives. And so what they've done in a lot of studies, and there's this huge 70-page paper that they did on this, is that they took a lot of these tests and reworded them. And so with all of these tests, I ask you, is it more likely that someone is this or this? Which is another way of saying, what is the percent likelihood that someone is this or this? And when you do these things with percent likelihoods, you get very similar effects. What Cosmides and Tubi did was, instead, what was changing the language, moving the language away from single event probabilities. So for the first one, like the question of Linda, the bank teller, they would give this the same description, and then they'd say, so given a group of 100 people, how many of them are bank tellers, feminists, or feminists and bank tellers? And they've done, like, they reorder the questions, they've done a lot of manipulations that make their findings pretty robust, and again they find that the conjunction fallacy essentially goes away. When you do these frequency questions across the board, people are far more likely to answer appropriately. They take into account base rates, they ignore the conjunction fallacy, and what I think is most surprising is that they're no longer overconfident about their answers, about the correctness of their answers. A little aside here, overconfidence is like any decision that you make, you are going to be more confident in the correctness of that decision than you should be. And like the only statement I feel I can make that is even close to being calibrated with how correct it is in terms of how confident I am is that we're all overconfident all the time. We have just really no way of judging how right we are, but we always assume we're more confident, except for a very interesting part of a distribution that doesn't, but that's for another day. And so if you're able to get rid of overconfidence effects, you're affecting something really deep. And that's a really powerful finding and not one to be overlooked. So what this suggests then is that we do have some understanding of these statistical laws, but how you access them is somewhat difficult. That you can't just pose a random question and expect people to access their statistical reasoning module, if you will, or just this is how they tie into that concept of evolutionary psychology. They believe that that our statistical reasoning set operates in a separate module away from all of our other logical reasoning. And I have a lot of issues with mental modules, but that's again a talk for another day. But the reason they're here and not here is because, and certainly not here, is because they say like, yeah, they admit we do make errors, but that's because the information isn't presented to us in a way that we can access our statistical reasoning. So for them, it's a problem of recall. You can't use the laws that are intuitively there in our long-term memory because we have no cues to retrieve them. And if we don't have the cues to retrieve them, then we're not going to. So where do we go from here? We have these two opposing views. So we've now crossed out these guys who are wrong. And so now we've narrowed the spectrum down to about here. So how do we narrow it down? There's another researcher who I'm a big fan of. His name is Gerd Gigerenzer, and he's founded this school of thought called bounded rationality. And basically, bounded rationality takes the idea that we do have some rational stuff going on, but it's hard to. We do have the ability to think rationally, but the universe is infinitely complex, and there's a lot of variables and error terms that get thrown our way, and we have a really hard time actually using this information. So what we do is we limit the scope of complexity in the universe, and we cut out a lot of variables that we think we can, and we pare down the information. We pare down the information available to us, to a few essentials that we can actually compute. And of the information that's left, the answers that we give based on that are rational answers. They are normatively correct. They are normatively irrational when you take a huge set of all of the universe's complexity. But we can't deal with that. There's no way we can process it, so we have to start small and then work from there. And the reason this falls somewhere in between here is because it's saying that, yeah, like we kind of have stuff like this, but it's only, we're not truly rational beings, we're rational for limited contexts. And they're not here because it's saying, we do have some concept of rationality here. That isn't just using heuristics because they're a shortcut or because we don't know how else to think. So I'm going to go over some of the evidence for that, and then we'll see where that takes us. So Gigerenzer does a lot of computer modeling because a lot of his work is just showing that these heuristics that he's talking about and these bounded rationality techniques are normatively rational. They are examples of Bayesian reasoning, but how that translates into actual human subjects is still a matter for debate. There's some evidence which I'll talk about with you, but what I'm talking about right now is purely done with computer models, because that way you can get huge data sets and make really powerful statements. So his most famous heuristic, and he is talking about heuristics, because again, heuristics are like taking out a lot of information and paring it down to some kind of essentials. His most famous one is called take the best. And the way take the best works is, so you're trying to decide, again, like for all these things, you're trying to decide between the likelihood of one probability over another. So we're just talking about two outcomes because it's easier that way. So you've got outcome A, and this process also works for any kind of decision making, where it's just choose one or the other. So you've got outcome or choice A and outcome or choice B, and let's say let's say A and B are cars, and you're trying to figure out which car you want to buy. So A and B each have this huge amount of, we have a lot of data about them. We know how much they cost, we know their size, we know how well they handle, we know their mileage, we know how they look, etc. And so we can stack these up as bits of information that we can then pair. They're directly comparable, so we can pair them against each other. And when we're asked when we're just asked a question of like, which do you want to buy, the actual question there is, of the properties of these two different cars, which properties are most important to you, and which car embodies most of those properties. And so there are two operations there. The first is you have to sort these in proper order. So let's say cost is your first concern, and maybe cost is how you gotten rid of possibilities C, D, and E because they were too expensive. So cost now is taken care of. And then you have like, well, maybe mileage is more important because I'm trying to reduce my environmental impact, and handling isn't that important because I don't really drive that aggressively. And so now, okay, so now we've got like miles per gallon, looks, handling. And that is how you organize those cues. And then the next question is which option has more of what you want, basically. And you make your decision. And there's a couple of different models for how that can work. One model is that you add up. Like let's say you assign points to these different things. Okay, so size is the most. If miles per gallon is the most important element, I'm going to assign that a high weight. And if handling isn't very important, I'm going to assign that a low weight. And then whatever score they get, you assign that weight, and then you develop what's called a linear model, where you have just a bunch of different terms with appropriate weights, and that produces a line graph. And basically, whichever's higher you pick. And that's a process I'll get to in a little bit. What Gigerenzer suggests is that, no, instead of doing any of that, because that takes a long time, and trying to figure out how to assign weights to these things, we can't even figure out how much 2 plus 2 equals all the time. We're not going to figure this out. That's a really inefficient strategy. So instead, what we do is we take the best. So in this case, we've already ruled out C, D, and E, and we know that miles per gallon is our most important. Which has higher miles per gallon? Oh, look, it's B. B's the car I go with. That's simple. And it's really fast, and it's a really powerful strategy because it means you don't have to spend a lot of time, and it means that you're you're making your choice based on the most important